right, so we're going to go through some example problems where we can use our conservation of energy equation. So we have here a simple pendulum is made with a mass of 2 kilograms. So we have a string that's 2 meters long. The mass down here at the bottom is 2 kilograms. A pendulum will swing back and forth through an arc. Its lowest position down here, and then it swings back and forth between 2 points. The problem is telling us the mass has a speed, so a v of 3 meters per second. When the pendulum is 30 centimeters above its lowest position. So lowest position, I'm going to call y equals 0. This is 30 centimeters. So at that moment in time, it has both kinetic energy and gravitational potential energy. The question is asking us for the maximum height above the lowest position. So it's going to swing up to a maximum height. The maximum height is the moment the speed is 0. So just like tossing a ball in the air, the ball slows down, slows down, slows down. At the maximum height, there's a split second during which the speed is 0. So it's essentially turning around. So we're trying to relate the speed and height at this first moment to the maximum height. And by the way, the pendulum could have been traveling in the other direction, and we could have found the maximum height on the other side. That's totally fine. It wouldn't have been higher, but it'd be the same height as we're drawing on the right side. So conservation of energy. Our full equation looks like this. So potential energy and kinetic energy at an initial moment in time, plus any work done by external forces, has to equal that final potential and kinetic energy plus the thermal energy. All right. So my initial moment in time, I'm going to go ahead and call this moment where I drew first, where we're saying we have an initial velocity of 3 meters per second and an initial height of 30 centimeters. At this moment in time, we do have gravitational potential energy because we are above that lowest point, which is where I defined 0 to be. We do have kinetic energy initially. At this final moment in time, over here, I'm choosing this maximum height to be the final moment because this is where I want to find the y final. We do know there is gravitational potential energy here because the mass of the pendulum is at a height y final above that lowest point, and we know there is no kinetic energy because at that moment, just that split second in time, the mass will not be moving. So these are the terms that go in for the potential and kinetic. Work external. Work external means work done by any force that's not gravity, not a spring, and not friction. Not kinetic friction specifically. We know there is tension acting on this ball the whole time. That's what's allowing it to swing back and forth like a pendulum. Work external would technically be the integral of this tension force dotted with the displacement. But again, the dot product the force needs to have a component in the direction of motion. In the case of tension, this always points inwards, points towards the center. The displacement at any given moment is tangent to the circle. That represents the direction the ball is headed in. So the dot product requires parallel components, but a vector that points towards the center is always perpendicular to the line that's tangent to the circle. So the tension does not do any work. It is not responsible directly for changing the energy. It's causing a change in direction, but not a change in speed. So in this particular case, we actually do not have any work done by external forces. Delta E thermal is also zero because thermal energy is created when an object slides on another surface. The pendulum's not sliding. So we can set the initial potential and kinetic energy equal to the final potential and kinetic energy. I'm going to go ahead and pull these over. We already described that the initial potential energy was mgy, the initial kinetic energy 1/2 mv squared. These together represent the total energy of this system. Well, that total energy still has to be there finally. We know there is no kinetic energy at this final moment we've chosen. It is all gravitational potential energy. So this kinetic energy we had has now become potential energy. So this is essentially what we're going to mean by our symbolic equation. So similar to last section, where we had a free body diagram and then our symbolic equation that wrote out all those forces in the free body diagram in terms of acceleration. We don't necessarily need a free body diagram per se, but we do need a way to reason through which of these energy terms we have in any given problem. And then our symbolic equation is plugging those values in. Now to continue solving, we're looking for y final. It turns out the mass doesn't actually matter. It ends up canceling. We know g, we know y initial, we know that initial speed, so we can solve for y final. Y final, when we divide by g, we're going to get y initial plus v initial squared over 2g. Now, SI units, we do want our height to be in meters, so 0.3 meters plus our speed is already in meters per second, which is what we want. Plugging this in. .759 meters. Oh, we only have 2 sig figs? Okay, so 0.76 meters will be the maximum height. So 0.76 meters, maximum height above that lowest point in the swing. Conservation of energy, we could totally do net work equals change in kinetic energy. That is equivalent. I personally like conservation of energy better, so I will be doing them mainly that way.